Hey everyone, and welcome to today's explainer. So, have you ever actually stopped to wonder how a chaotic, messy jumble of code somehow becomes a reliable, polished piece of software? You know, the kind that millions of people can use all at once without the whole thing just crashing to the ground. Well, I can tell you for sure that doesn't happen by accident. Today, we're going to build a really solid foundational understanding of the engineering principles that make that kind of transformation possible.
Okay, let's just dive right into our roadmap for today. We'll start off by welcoming you to software engineering and contrasting it with hardware, then we'll check out the technology stack. After that, we'll map out the process framework, and finally, we'll track the whole evolution from the classic waterfall model all the way to modern agility and XP. Let's get to it.
All right, part one, welcome to software engineering. We kind of need to define our core subject before we start building on top of it, right?
So, according to the IEEE, software engineering is, and I quote, the application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. I really want you to focus on those two words right there, systematic and disciplined. Because honestly, this is what separates true engineering from just, casually sitting down at your keyboard at 2 a.m. and hacking together some code. It's about bringing order, measurement, and long-term maintenance to the entire life cycle of whatever it is we're building. Let's put this into perspective to really hammer it home. Think about the difference between a simple program and a full-blown software product. A program is usually something pretty small. It's like a quick little sorting script you write for yourself on a Sunday afternoon. It does one thing, it has limited functionality, and you are literally the only user. But a software product, that is a whole different beast. It's built by a coordinated team for multiple users. It includes comprehensive documentation, system requirement specifications, user manuals, a polished graphical user interface, the whole shebang. You just can't hack together a massive word processing software by yourself in a weekend. It absolutely requires that systematic approach we just talked about. Moving right along to section 2, software versus hardware. It's time to mentally separate the physical machines from the digital code. There is this absolutely fantastic quote from our source material that highlights a crucial distinction here. It says, software is engineered, not manufactured, and it doesn't wear out. Think about that for a second. When physical hardware is manufactured, quality problems can totally get introduced on the assembly line. But with software, if the original design is good, the replication is literally perfect every single time. Plus, and this is huge, if a physical gear breaks, you just grab a spare part. But there are absolutely no spare parts for software. If a line of code is broken, we have to engineer a completely new fix. The hardware bathtub curve perfectly illustrates what I'm talking about here. It shows early failures from manufacturing defects, then a nice long period of steady operation, and finally a huge spike at the end as the machine physically wears out. But contrast that with software. Theoretically, software should have this perfect idealized curve. We fix the early bugs, and then it just runs flawlessly forever because, well, it doesn't wear out. But in reality... Okay, section 3, the layered technology stack. Let's look at the actual structural framework here. Imagine software engineering is like building a house, right? You've got to build it layer by layer. At the very bedrock of this approach, we have a quality focus. Disciplined quality management is the foundation that literally everything else rests on. Without it, the house crumbles. Above that is the process layer. That's the framework holding everything together and making sure we deliver on time. Then we have methods, which are the technical how-tos, how we analyze, design, and actually write the code. And finally, at the very top, we have our tools, which we use to automate the process. But here's the catch. You can't just go out, buy a fancy new coding tool and expect magic. You absolutely need the methods, the process, and that bedrock of quality underneath it for it to actually work. Which brings us to section 4, core process framework activities. No matter what kind of software you're building, there is a generic process framework that pretty much everyone follows. It boils down to 5 sequential steps. First up is communication. You got to sit down, talk to the stakeholders, and figure out what they actually want. Second is planning, where you lay out your schedule and map out any technical risks. Third is modeling. That's analyzing and designing the architecture. Fourth is construction. And hey, notice something here. This is the very first time we actually write a line of code or do any testing. Finally, step 5 is deployment, where the software is delivered and evaluated. Honestly, a massive rookie mistake novice engineers make is jumping straight to step 4, construction, without doing any of the communication or planning first. It's a recipe for disaster. All right, section 5, the classic prescriptive waterfall model. Let's take a little trip back in time and look at the oldest paradigm.
Now, what's really interesting about Winston Royce's 1970 waterfall model is how incredibly rigid it is. It takes those 5 core activities we just talked about and forces them into this strict, linear downward flow. You start at the top with requirements analysis, and you flow downward, like a waterfall, obviously, through design, implementation, testing, and finally maintenance. The defining characteristic of this old-school model is that every single phase has strict entry and exit criteria. You have to completely finish your requirements, freeze them solid, and only then do you get to move on to design.
But this brings up a massive kind of Socratic question for you to ponder. What happens when the requirements suddenly change mid-project? Imagine you're 6 months deep into the design and coding phases, and your customer calls you up and realizes they need something completely different. In the rigid waterfall model, trying to go backwards against the flow of the waterfall is, well, it's pretty much impossible. It's incredibly difficult, wildly expensive, and just absolute chaos. This fatal flaw in the linear model meant the industry desperately needed a new approach. So enter Section 6, Modern Agility and Extreme Programming. This is the industry's answer to the need for speed and flexibility. Contrast that rigid, locked-in waterfall with a tight, continuous feedback loop. Extreme programming, or XP, relies completely on rapid iteration. Instead of giant requirement documents, you plan using simple story cards written right there with the customer. You keep the design super simple, then you jump into this rapid-fire loop of coding and testing. XP uses some really cool practices like pair programming, where 2 developers sit at one machine so they can constantly review each other's code, along with continuous integration. The entire focus here is on delivering a working piece of software as quickly as possible, rather than getting bogged down in heavy, unchangeable documentation. So the crucial point here is that to make this incredibly rapid, flexible style actually work, an XP team absolutely has to stick to 5 core values. They need constant communication with each other and the customer. They have to embrace simplicity, basically maximizing the amount of work not done. They rely on nonstop feedback through testing. They've got to treat each other with respect. But honestly, perhaps the most important one is courage. Think about it. It takes serious courage to look at a block of code you just spent 3 days writing, realize the customer's needs have shifted, and just throw it away. To completely change the design so you can build the right thing today, that takes guts. Which leaves us with this final thought to wrap up today's explainer. We established earlier that software doesn't physically wear out like hardware does. But as we just learned through Agile, software development is this endless, looping cycle of continuous feedback, shifting requirements, and rolling out new updates. So, if it never wears out, but it never stops changing, are we ever truly finished building a piece of software? It's a pretty provocative thought about the living, breathing nature of software engineering, isn't it? Thank you so much for joining me for today's explainer, and hey, keep building.